So hello, good evening everyone. Am I audible? Hello. Good evening everyone. Am I audible?
Yes, sir.
Okay. So my screen is visible, right?
Yes, sir. Visible.
Okay, you can see the question.
Sir, can you zoom? Hello?
Huh.
Can you zoom the screen, sir? It's visible but hard to see.
Okay. Now is it visible?
Perfect, sir.
Okay. Okay, so this was the question from GATE 2007, I think. Yes. So here we have to calculate the metal M melts at 1000 Kelvin with an enthalpy of fusion of 10 kilojoule per mole. Specific heat capacity of solid and liquid are respectively Cp 20 joule per Kelvin for solid and 30 joule per Kelvin for liquid. So we have to calculate the enthalpy change for liquid to solid transformation associated with the liquid to solid transformation at 900 Kelvin. So this is not a typical question. So usually what we do, we know the enthalpy change. It's Cp from T1 to T2 when there is no phase transformation is involved. But here there is an undercooling is associated. So that means we first have to understand the, suppose we draw the enthalpy versus T. Okay, so we know that the curve will be something like this. So this slope will be higher than this slope. Can anyone tell why? So this is our liquid phase, this is our solid phase, this part, this is the enthalpy of fusion, latent rate of fusion that we say. People keep joining. Okay. So we know that dH by dt equal to Cp. So the slope of this line, and this line, that will be Cp. Okay, we know that this is for liquid phase, this is for the solid phase. So Cp of liquid is always higher than Cp of solid. So that's why the slope is higher than this slope. Okay, so now suppose this is our melting point Tm. So here it has asked that the metal melts at 1000 Kelvin. So this is our 1000 Kelvin. Okay.
Hello.
Huh?
Sir, your cursor is not move.
Which one?
सर सर जो आप बता रहे हो उसमें जो कर्सर है मूव नहीं हो रहा है.
अच्छा. तो इसका तुम्हें मतलब पता है? डू यू नो दिस कर्व H वर्सेस T?
सर जो आप दिखा रहे हो मतलब कि राइट लाइन से जो स्केच किया है वो शो हुआ है और जो आप 1000 केल्विन जो बता रहे हो उसमें जो मेंशन कर रहे हो ना वो मतलब बता रहे होंगे आप में स्केच करके वो दिखा रहा नहीं है.
दिखा नहीं रहा है. So 1000 Kelvin, that is not visible.
सर ये dTh upon dt equal to Cp and Cp liquid greater than Cp solid ये दिखाया मुझे अभी.
अच्छा, 1000 Kelvin दिखा नहीं रहा है.
हाँ सर ये अभी दिखाया डॉटेड लाइन में मेल्टिंग पॉइंट.
हाँ, मेल्टिंग पॉइंट है. So which screen is better, this one or I mean should I keep like this?
यस सर अभी कर्सर मूव हो रहा है.
Okay, okay, okay. So what we have to do is we have to draw a line like this because it has asked that we have to calculate the enthalpy change when it is undercooled. So undercooled means suppose this is a 1000 Kelvin, somewhere this is our 900 Kelvin. So at 900 Kelvin it has asked to calculate the enthalpy change. So we have to consider this liquid curve that is extrapolated towards this side beyond the melting point, and here we can draw this is our liquid, this is our solid. So to calculate this enthalpy change. Okay, so what we do, we know that enthalpy is a state function. Okay, so enthalpy is a state function. So is it visible now?
Yes sir.
Okay.
Yes, sir.
So either we can calculate from this way, from direct here to here, but there is no way we can calculate this, so we can go like this. From L2 we go this way, this is one path, then we come this way downwards, again we go this way. So this is similar to going from here to here. Okay, we are taking, because the state function, it depends only on the initial and final position, doesn't depend on the path. Okay, so this type of question, when undercooling is involved, we have to solve it like this. We cannot directly use this. This will give wrong answer. So I'll draw that again in the new slide. It is the Cp of liquid 30 joule per Kelvin. Okay, so now suppose this is A to B direct path, and here we can say A to C, C to D, then D to B. So we'll calculate like this: A to C plus C to D plus D to B. Okay, so as we are going from liquid to solid state, so we know that when a liquid solidifies, so liquid has some excess enthalpy, that is this is enthalpy of fusion, so that has to be rejected in order to transform to solid. So we take this as negative, because this energy, this has to be rejected in order to solidify the thing. So what we do, so first here 900 to 1000 Cp of liquid dt, 900 to 1000. Okay, then minus del HF. So as I said, because we are going from liquid to solid, we have to reject the enthalpy of fusion, then only we can solidify that. So this is a minus sign. Then again plus, we have to go from D to B, from D to B. So 1000 to 900 Cp of solid, because this is the solid line dt. So is this clear? Everyone got it?
Yes, sir.
So now we just have to integrate this. Can anyone calculate and tell me the answer? Just you have to put dt, 1000 minus 900 minus 10,000 plus 20, 900 minus 1000. Okay, so this will come something around 9000 joule. So then in the second part we have to calculate the entropy change, exactly similar except we know the entropy change, that is Cp by Tdt. Okay, so just in case of Cp we have to just put everywhere Cp by T we have to do, and this here we have to take the temperature at which we are doing this. So this is 900 Kelvin. So just have to put this T here, and then integrate dt by t, that is ln t. So ln 30 ln 1000 by 900 minus this plus 20 ln 900 by 1000. Okay, so here I did one mistake. This has to be 1000 because we have to use the melting point. Because the melting point, it is given that it is 1000 Kelvin. Okay. So if you have any doubts, then please ask me in this question, in calculation or in the concept. Every time there is an undercooling associated, you have to go like this cyclic way. You cannot directly use this formula. So this is the right answer. This is the right answer.
Sir,
हाँ
sir, one thing explain please. In the case of undercooling, we have to add or subtract because sometimes I got confused in this.
which
Uh,
one? Which one?
where we are in the case of undercooling, we are adding extra amount of energy when the phase is transformed. So I am asking to That please explain when we add or subtract this amount of energy.
Okay, this latent rate of fusion.
Yeah.
Okay. So we know that why this is because when we take liquid, there is more open structure as compared to that of solid. So if we supply some energy, then what happens? The atoms that are in liquid that can vibrate more as compared to that of liquid, because in solid we have a compact structure. So atoms cannot vibrate more. So if they cannot vibrate more, they cannot absorb more energy. So the Cp is less. Cp is basically the amount of energy that is required to increase the temperature by 1 degree. So that is why, because liquid has open structure, it can vibrate more. So as it can vibrate more, it can absorb more energy. So the Cp of liquid is higher. So liquid has some extra energy that has to be extracted when it is transforming into solid. So that extra energy, that is this latent rate of fusion. So this has to be removed from the liquid in order to solidify. Okay, so when we are going from liquid to solid, okay, so this energy has to be released. We have to extract this, or we have to deduct this energy from liquid in order to solidify. So that is why when liquid to solid we go, we take this as negative. But when we go from solid to liquid, then we have to add this energy, because solid has less energy. We have to add this extra energy in order to form the liquid. So when we're considering a transformation that is solid to liquid, in that case the latent heat of fusion will be positive. So in the question it is given that liquid to solid, so that is why we use negative. If it was given solid to liquid, then we have to add this. So is it clear? So every time you see the question, if it is given liquid to solid, then you always take this del HF for latent heat of fusion as negative, because we are removing that energy from liquid. Okay, so this question anyone had done before? New. So first I will go to the concept of nucleation. What is nucleation? Suppose we consider a single component system. Solid to liquid transformation. Okay. So we have this G versus T curve, that is something like this. This is our melting point. So as we know that the phase that contains minimum free energy is the stable phase. So above the melting point, liquid has the minimum free energy, that's why liquid is stable, and below the melting point, solid has minimum free energy, so solid is stable. And the slope of this line, if you consider, so we know that G equal to H minus Ts. So if we plot G versus T, then the slope will be minus S. So this line slope, this or this, both are minuses. So why it is not constant? Because if you consider entropy is related to Cp. So Cp, as we know, Cp curve, that is something like this. With increasing temperature, Cp increases up to 3R, and then it becomes constant, almost constant. So because Cp is increasing with temperature, so the slope cannot be constant, so we have a curved line, and where it cuts this will be our H enthalpy at T equal to 0. Okay, so now suppose, to understand the concept of nucleation, suppose we are considering a temperature that is lower than the melting point, and we have a container where initially we have liquid. So that transforms into one solid particle in the center, spherical particle, and the volume of this is VL. This is Vs, volume of solid. So the remaining part, what will be the volume of this? VL minus Vs. Okay. So suppose this has certain free energy, that is GL. This solid has certain free energy, that is GS. Okay, so for one, total free energy will be volume times the free energy of liquid. For B, VL minus Vs, that is the liquid volume of the liquid, into GL plus Vs into Gs. So is it clear till now? What is VL? What is GL? So this GL, Gs are basically this. Free energy of liquid and solid. At any temperature, we have a specific value of this free energy of solid or free energy of liquid. So here, at whatever temperature we have considered, at this temperature, we have certain GL for liquid and Gs for solid. Now we have to think that as we created the solid inside a liquid, there is an interfacial area that is created. So that requires some extra energy. So that we have to consider as okay. So this is the interfacial area that is required to create this new surface, solid liquid interface, that is this. So we have to multiply this by the area of the solid, the surface area of this. So that gives the area free energy or the surface energy. So what will be our del G, change in free energy? Suppose this is our G1 and this is our G2. So del G will be G2 minus G1, because always you know product minus the reactant. So the product is your solid, the reactant is liquid. So we take this way. So I'm just rearranging this. Bl minus Bs into Gl plus Bs Gs, this one, plus A gamma Sl minus Bl Gl. That's it. So now I open this, minus Bs Gl plus Bs Gs plus A gamma Sl, because one will cancel out. This Bl Gl, here Bl Gl, Bl Gl, this will cancel out. So this will be finally Bs So this is the final form, Bs Gs minus Gl plus A gamma Sl. So if we consider a spherical particle, okay, suppose we are considering a spherical particle is nucleating. So here what we take, delta G equal to the volume of the spherical particle is 4 by 3 pi r cube to delta GV. So what is this delta GV? This is basically this, here we have seen Gs minus Gl. And the surface area of the sphere is 4 pi r square into gamma Sl. And always remember, so this should be this value. This is basically for any temperature of consideration. This is our delta GV. Okay, and this has to be negative because we know that the free energy, whichever has the minimum free energy, so that phase is ready to transform. So here only we can see that liquid can transform to solid, because that way only the free energy will decrease. So this is always negative. This is the driving force. This is the excess energy that is required. So until this value, this whole value is greater than this value, we cannot have nucleation. So if you want to calculate the critical radius and the critical value of this del G, that is the barrier, nucleation barrier, we can just differentiate this. And we have to put this equal to 0. So just you have to differentiate this and put the value to 0. You get the value of this R star, that is minus 2 gamma Sl by del GV. So what is del GV? That is also del H del T by Tm. This also you remember, important question. This is the latent rate of fusion, del HF you can write. This is the undercooling and this is the melting point, or any transformation temperature that has given. Like for suppose solid, there is one transformation temperature that may not be the melting point. So there you have to use the transformation temperature, T melting or T transformation. Then how do you calculate the delta G star? So you have to put just this value of R star in this equation, in this here, equation 1 suppose. So you have to put the sorry value of R star in this equation. So remember these three equations, these are very important. every year 1 or 2 questions from this relations are compulsory. R star, delta G star and delta GV. Now we plot this R versus delta G. So what we get, the volume free energy or the driving force that we say, that is 4 by 3 pi r cubed LGB for spherical particles. So that will go something like this, always negative. And the surface energy 4 pi r square gamma SL, so that will go something like this. So the resultant will be something like this. Okay, so this is at the highest point. So this value is a delta G star and this is our R star, critical radius and critical nucleation barrier. So any doubts till now? Okay, so now I'll go to the question. So here it is given to calculate the critical nucleus size in nanometer when copper melt is undercooled by 100 Kelvin. So undercooling is basically, suppose this is our melting point, del T 100 Kelvin means this is our del T, this is our 900 Kelvin. Okay, if we assume this is 1000, then this is 900. So del T is given, melting point 1356 Kelvin, that is given. Density is given. Interfacial air energy of solid and liquid 0.5 joule per meter square. Delta HF is given. And molar volume, that is 7 × 10⁻⁶ meter cube per mole. Okay, so how to calculate this? So as I have shown here, del GV, what is this? First we have to calculate this del GV, then we have to put it here in R star. Okay, so first we will calculate delta GV, that is del H del T by Tm. So what is del H here? And always remember the unit of del GV is joules per meter cube, always. So but here it is given joule per mole, delta HF, so we have to convert this to joule per meter cube. That's why this molar volume is given. 13,000, that is our del HF, into delta T, that is 100 Kelvin, melting point 1356. So this value we get in joule per mole. So here what we do, the molar volume is given 7 × 10⁻⁶ meter cube per mole. So this is a mistake, this should not be negative, this is meter cube per mole. So we already have unit of joule per mole. So how can you get this into joule per meter cube? So if we get this, then this mole and mole will cancel and we get joule per meter cube. So we just have to divide this. So this is an important step. We have to just divide the molar volume by whole of this. So can anyone calculate and tell me what is this value?
Nine point five eight into 10⁸
It is a value 9.5 into 10⁸. I think there is a mistake. Let me check. So I think this will be very big value, like so as per my calculations it comes out this value delta GV joule per meter
Yes,
cube.
sir, same.
Okay, so we got del GV, then we know R star from here minus 2 gamma by del GV. So we just have to put that. What is the value of gamma? I think 0.5. Yes. So this will come close to 7.3 nanometers. And one thing you must know, so we have delta G versus R curve. Suppose we are given at three temperatures T1, T2, T3. T1 is greater than T2 greater than T3. So how do you think this curve will vary if we change the temperature? One will be like this. So which one do you think belongs to which temperature? How to check that? So here you have to understand eraser is not working. Fine. So here you have to understand that if we increase the temperature, what are we doing? Like here I have shown, if we had initially we had at this temperature and then we go to this temperature, so undercooling initially was this full. So as we increase the temperature, the undercooling is now this. So we are decreasing the undercooling as we go to higher and higher temperatures. Okay, so as temperature increases, undercooling decreases. Okay, so what happens when undercooling decreases? So this is our undercooling. So what will happen to delta G star when we decrease the undercooling? So we know that delta G star equal to 16 pi gamma SL cube by 3 delta GB square. Okay, so here in delta GB term, that contains the delta T term. We know delta GB equal to del H del T by Tm. So delta GB is directly proportional to undercooling delta T. So here it is as in denominator. So delta G star is inversely proportional to del T. Okay, so as we decrease the del T, delta G star will increase. Are you getting my point?
Yes, sir.
Okay, so as we are considering three temperatures, So this will be for T1, this is for T2, and this is for T3. Why? Because as we said, T1 greater than T2 greater than T3. So T1 is the highest temperature. Highest temperature means lowest undercooling. So undercooling low means delta Gb is low, because undercooling is delta Gb is directly proportional to undercooling. So lowest delta Gb means highest del G star. So we see here we have highest value of delta G star. T2 smaller, so relatively delta T will be larger as compared to T1. So this will be in the middle. And T3 is the lowest temperature, that means highest undercooling. So undercooling highest means delta Gb highest means delta G star lowest. So this small value. So remember this is very important. So everyone got what I have said till now, or if you have any questions you can ask me. Okay, so thank you for joining. See you next week.
Thank you, sir.
Thank you, sir.
Thank you.